Yes, it's the guy. In this video, we are going to talk about macrolides as a class of antimicrobial. Here is the summary of what we are going to talk about. We are going to introduce our topic. We talk about the genome structure, pKa and solubility, formulations. We talk about the salts and esters, chemical properties, where we have the acid stability, mechanism of action, resistance, cross-resistance, erythromycin analogs, drug interactions, indications, and adverse drug reactions. Please don't forget to subscribe, like the video, and share. Let's begin. Macrolides, one, they are narrow spectrum. They are narrow spectrum, mainly active against the aerobic gram positives. They also have activity against mycobacteria and a few gram negatives. They are beta. So most of them are formulated as coated tablets for the oral formulation, also as suspensions. To mask that beta test. They are protein synthesis inhibitors. They are protein synthesis inhibitors and primarily they are bacteriostatic. About the genome structure, yes, same kind of guy. About the genome structure, we need to know that macrolides, we have the 16-membered lactone ring macrolides and the 14-membered. They are called macrolides because they have the macrocyclic lactone ring. So the ring, there is a 14-membered lactone ring and a 16-membered lactone ring. An example here is the tyrosine. It is mainly used in agriculture. Those animals, the goats, cows, sheep, in treatment of infections like mastitis, diarrhea, GIT inflammation. In 14-membered, we have an example, the prototype, which is erythromycin. We are going to talk about erythromycin, its structure, such that we can easily understand the modifications which were made to make other macrolides. But the prototype is the erythromycin. We are going to use these structures to easily remember the structure of erythromycin and also to know where the modifications were made to make other macrolides. One, we need to know that erythromycin is from propionic acid, which is the 3-carbon compound. We shall find some reductions oxidations, and addition of sugars. Propionic acid is a three-membered carbon structure. When you look at this structure, here it is one carbon, this is another carbon, and this is the third carbon. So we use the propionic acid moieties or the propionic acid residues to make the erythromycin. This is carbon 1, this is carbon 2, this is carbon 3. Even this one, this is 1, 2, 3. 1, 2, 3. What's done here? There is loss of the OH group. Even here there is loss of OH. Even here there is loss of OH group. Here there is loss of water. This is OH. Even here it is OH lost. Also here there is loss of OH group. Here there is loss of OH also. Even here there is loss of OH group. Here there is some changes that these two carbons are both outside the ring, but we are losing water instead. There is loss of water. Therefore, we shall have this structure like this. Here there is oxygen remaining, and we have O here. Up we have oxygen atom also. So from propionic acid, meaning at every second position we have a methyl group. So this is carbon 1. We shall have a methyl group here. These are joined. I should use black here. They are just joined. Here we join these two. At carbon 1 there is oxygen. So we expect this OH to be there. And a methyl at second position. OH here, a methyl at this position. I can't draw it to the inside. Of course, it looks weird. Then we expect the OH here. And a methyl here. But at this position, as we said, there is reduction. This is carbon 1. This is 1. This is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It's a 14-membered lactone ring. At position 7, there is reduction. So in erythromycin, this position 7, there is reduction. So this OH group is no longer there. We have hydrogen atoms, so it won't be there. Also, there is oxidation at position 6 here. There is oxidation. So you'll find that, okay, these are hydrogens. There is OH group here, which wasn't there in propionic acid. Also, say this is carbon 1, is O. At carbon 2, you expect the methyl group. This is OH, you expect the methyl group here. Now here, we have this like that. Again, at carbon 12, at this carbon 12, okay, don't confuse them. This is 4, this part, oxidation for this part. At carbon 12, there is oxidation also. There is OH group introduced. We have that OH, meaning that here at carbon 12, there is oxidation. At carbon 12, they made oxidation. There is OH group. Also, these hydrogen atoms, they are substituted with sugars. These hydrogen atoms, these two. The normal sugar, the hexose, is like this. By the sugars we have here, we shall have the glutinose and the succinylate. The normal sugar is like this, carbon 1 up to carbon 6 with the OH groups. But for glutinose, we have this sugar substituted. It will be like this. It is a 2,6-deoxy hexose, meaning at position 2, the OH group was removed, so it's just hydrogen. There will be 2 hydrogen atoms. Also at position 6, there is no OH group, so we shall have only the methyl, the OH substituted with the hydrogen. Here we have the OH group. Here at position 3, there is a methyl group and a methoxy group, that is glutinose. And for the succinylate is a 2,4, is a 3,4,6 trideoxy. This one is a dideoxyhexose. This is a trideoxyhexose. For the succinylate, its structure is like this. Straight. At position 3, there is no OH group, but this is position 1, there is OH. This is position 2. At position 3, we have a dimethylamine for the succinylate. Then we said that position 4, there is no OH group, and position 6. So this one will be its structure. Now, these sugars, they are substituted here. Here we shall have the glutinose. Therefore, it should be like this. This is the position 1. This is the position. This is position 6. At position 5, there is OH group. At position, this is position 3, there is a methyl group and a methoxy group. Position 2, nothing is there. Then for the succinylate, here, position 1 is used to attach it here. This is it. At position 1, this is position 1, then position 2 is OH group. Then position 3, we have the dimethylamine. Position 4, nothing is there. Position 5, we have a methyl group. So this is the genome structure. This is the erythromycin. Substitutions, we said that it's made from propionic acid, as you have seen. There are some reductions at position. This is position 7, and we have oxidations at position 12 and position 6. Then the OH groups we are substituted with the sugar moieties. From propionic acid, we have that one. Also, this H group, this H, can be substituted to make esters. Can be substituted to make esters. Now, when we talk about the pKa and solubility, erythromycin is basic. These macrolides are basic because of this amino group. This amino group, the pKa is around 8, meaning that this one is slightly, or it is insoluble in water. Because the pH of water is around 7, and this one, the pKa is at 8, meaning that higher than this pKa, the pH higher than 8, there will be no dissociation. But below 8, we can have dissociation. But this 7 is nearer to the 8. So they are slightly insoluble in water. But they are soluble in organic solvent. In organic solvents. Because of this macrocytic lactone, which is more lipophilic. But because of this amino group, the pK is around 8, making it basic. Therefore, it is insoluble in water. For the salts, some salts can increase the solubility. We have the salts. Some can increase the water solubility, while others can decrease the water solubility. Let us see that